Suppose that I want to recognize two number, or in another word, two pattern, recognizing. For example, I want to recognize 7 in 10 or 11 in decimal binary. We know that 7 in decimal binary is equal to 0, 1, 1, 1 in, and 11 in 10 is equal to 1, 0, 1, 1 in 2 binary. Get it here? Yes, I want to calculate 7 and 11. Okay. Now I want to recognize both of them. Why I write these numbers in 4 binary? Do you know why I am writing these numbers in binary system in 4 bits? I cannot represent the 11 with 3 bits. Yes, I can represent the 7 with 3 bits. I can say that 7 is like that. But I cannot represent the 11 with the 3 bit. I need to 4 bit for representing the 11. For this reason, I have to represent the 7 also with 4 bits. Now, I want to design this, actually, my logic circuit. Look at here. We said that we have to convert the bit that is 0 to the 1. It means that if I write the logic equation of this pattern, what can I write?
B3 bar.
What?
B3.
B3 bar, yes.
Dot. B2.
Dot. B2.
B2 bar.
Dot B1. And dot B0.
Okay, and again for this P11, what can I write?
P3, P2 dot.
Yes.
And P0 and P0.
Not P1, P1. Thank you. What is your name?
Nigar.
Okay, thank you. Now, according to these two equations, I can design my circuit. First of all, I want to design P7. I know that I have 4 bits. It means that I have 4 input. The lower input is B0, B1. Let's don't write here. B0, B1, B2, and B3. I want to produce P7. And for P11, again, I have B3, B2, B1, and B0. Now, according to the equation, I know that B3 have to be converted. How can I convert it?
Using OR
NOT
gate.
gate. Not OR gate, NOT gate. What about this one? The B2.
B2.
With converting B2, I can produce P7 and P11. Now, I want to have one if one of them comes to the output. What kind of gate can I use here? Because I want to have one of them P7 or P11. If I use AND gate, what happened if I use AND gate? If I have this pattern, only here will be 1 and here always will be 0. If here is 1, always here will be 0. For this reason, I will have 1 and 0 here. So, because always one of these inputs will be 0, for this reason, I cannot use AND. If you look at here, you can design and draw your circuit like that and also like that. Now here you can see better than this one that always only we have 4 bits or 4 inputs for all of these circuits. For this reason, I cannot have 1 and 1 for both of these inputs at the same time. Okay, now, after learning about the designing of logic circuits, we want to learn how can we form a truth table from logic equation. First of all, how can we write a logic equation? I want to show you using sum of products, we can express a logic equations. Products is represented using AND gate, and sum of products is representing using OR gate. So first of all, we try to enclose groups of AND operators in a parenthesis, then evaluate each group of AND operations. After that, we can draw the truth table and write the output according to the logic equation that we have. For example, suppose that I have this logic equation. My equation is y is equal to a plus B dot C bar plus A bar dot B bar dot C. This is my equation. I want to draw the truss table. First of all, I have to determine the number of variables. How many variables do I have at this equation? And 3. A, B, C. 1, 2, 3. Now I have to write all of the possible patterns. Let's write it. Yes. We will have 8 pattern. I write these patterns. Now, according to this equation, I want to find the y. Look at here, we said that, we said that we enclose groups of AND operators in parentheses. Then express logic equation as a sum of products. What is the meaning sum of products? First of all, I want to enclose the AND operation in a parenthesis. Then and this one, that's it. Now I could represent the equation as a sum of products. It means that I have AND gate here, AND gate here, and this is a one variable. So all of them is OR with together. If I want to draw it, I can write, I have how many variables? A, B, and C. I have B bar, it means that I have NOT gate. I have also C bar, it means that I have NOT gate, because here is C, B bar, and here is C bar. I don't have A, yes, I have A bar. I have also A bar. Now I produce both of them. A bar, B, B bar, C, C bar. So first of all, I produce the variables which products inside of the parentheses. B dot C bar and with together. Now I draw the AND gate. B, here is B. C bar, it can be better if I write it like that. Bu xətlərin heç əhəmiyyəti yoxdur, hardan və necə çəkirsiniz. And C bar. Now the output of this AND gate is B dot C bar. The second AND, A bar, B bar, C. For example, if I draw it here, A bar, B bar, because here is B bar, C. C can have to comes from here. And here I will have A bar, B bar C. Now, suppose that this is this output, this is this output, and also I have A and or all of them. I or all of them. Now this is my Y. I could design or produce my circuit, logic circuit, according to the logic equation. Now let's calculate the Y. Let's calculate the output of this equation and also this circuit. If all of my inputs be 0, what about this one?
Also 0.
صفر.
Yes, 0.
Also 0. Why?
Because we get 0 times 1.
Exactly. Because we get B and 0 and 1. Why? Because I have the complement of C. The complement of C means if my C is 0, I will have 1. And also B is 0, it doesn't matter. This is the and if I have only 1 0, this result will be 0. What about this one? Again,
0.
0 for the same reason. Because if I look at here, I can find that one of these variable will be 0 and I have AND gates, I have 0. So 0 plus 0 plus 0 will be what? 0. This one will be 0, 0, and 0. So my output will be 0. Now, what about 0, 0, 1? Yeah, çok rahat. You can say that because this parenthesis, the result of this parenthesis will be 1, and I have also or, it doesn't matter the rest of the equation. I will have 1. What about 0, 1, 0?
1.
1.
Again 1. Again 1. A bar will be 1. Let's talk about this one. B, C bar. B is 1. C is C complement 1. Again, this term is 1. This is 1. What about 0, 1, 1?
0.
0.
0, exactly. Good. What about 1, 0, 0?
1.
1.
1.
A is 1. It doesn't matter the rest of the equation because I have or. That's it. I could find the output according to the equation, and also I can design the logic circuit, and according to the logic circuit I can also find the Y truss table of this equation and this circuit. And here I also write the truss table and explain the reason why the output is 0 and 1. You can learn and find them. Now we have two important laws in the logic equation that we need to learn. First of one, first of these two law is distributive law. What does it say? The distributive law says that if I have A dot B plus C, A dot B plus C, I can multiply or AND. Let's don't say multiply. Here, in the case of logic equation, we use AND. If I have this term, I can write that A dot B, A and B, or A and C. Again, I can enclose it to the parentheses plus A and C. But in the case of OR, I cannot write that because the right-hand side of equation and the left-hand side of the equation are not equal together. Only if I have AND operation, I can use distributive law. I can distribute this equation. For example, if I have A dot B plus C bar, I can write A dot A and B or A and C bar. So I can design the logic circuit according to this equation because we need to express the logic equation as the sum of products. Again, according to the logic equation, we can find logic circuits and trust table. According to the trust table, we can write logic equation and logic circuits, and so on. Now, in designing a logic circuits, the most important thing is that we always try to design efficient logic circuits. Efficient logic circuit. Designing the efficient logic circuit is so important because of the time of the efficient, the time to response the efficient circuit is better than the other one. And also in the efficient logic circuit, we use more, actually little than the gates that we use in the efficient logic circuit, and so on. As you see here, this is a logic circuit, and this is a trust table of this circuit. If I look at to the output of this trust table, I can find that in the case of 2 bits, my output is 1110. 1110, this Y. If I notice to this output, I can find that if I complement the output, the result will be 0001. This output is the output of AND gate. 0001 is output of AND gate. It means that if I complement the output of this circuit, I can find the output of the AND. So it means that instead of this circuit, I can use only AND gate and complement the output. so I can find the same output. Another law that is so important in the case of logic circuits is De Morgan's law. De Morgan's law. De Morgan's law says that if I have A dot B bar, instead of this term, I can write A bar plus B bar. And if I have A plus B bar, it means that I have A bar dot B bar. A bar dot B bar. Now, as application of logic circuits, let's talk about the 7-segment display driver. A digital display used in clocks, scales, smart sensors, and all of the other digital devices. For representing the numbers in the 7-segment display, why we call it 7-segment? Do you know why we call it 7-segment?
Because there are 7 letters in it.
7 what? So for representing, how many numbers can I represent with the 7-segment?
10.
10.
No.
11.
From 0 to 9.
Yes, 0 to 9, up to 9. 10 numbers can I represent, but the last number is 9. It means that how many bits do I need to represent the numbers? Exactly, using 4 bits, because I have 0 up to 9. Now, because for representing 9, the minimum bits that I need are 4 bits. It means that all of the numbers from 0 up to 9 have to be represented with 4 bits. But if I use 4 bits, if I use 4 bits, B3, B2, B1, B0, I will have 0 up to 15. It means that I will have 16 number patterns. But I only can represent the numbers up from 0 up to 9. What happened for the another patterns? In this case, we say that from 10 up to 15, all of the outputs is don't care. It is don't care. It doesn't matter. We only used 0 up to 9. Now, if you look at here, we named all of these LEDs. Each segment is LED. LED. We called them like that: A, B, C, D, E, F, and G. Now, if I have to have 0, I need to light this LED, this LED, this one, this one, this one, this one. It means that A, B, C, D, E, F have to turn on. What is the meaning of lighting the A? It means that I have to have 1. Only the G will be 0. The other LEDs will be 1. If I have 1, it means that I can represent the 0. A, B, C, D, E, F, G. 1, 1, 1, 1, 1. Only that G is 0. In the case of 1, again, I look at to the LEDs. I can find that for representing 1, I need to turn on the B and C LED. For the B and C, I write 1. Other LEDs will be 0. For the same way, for 2, I look at here, A, B, G, E, and D will be 1. 1, 1, 1, 1, 1. Now, I have to design a logic circuit for 0, for 1, for 2, and so on. If I draw the truss table of 7 segments, I can find that for 4 bits, I will have 1, 2, 3, 4, 5, 6, 7 outputs. Because at each pattern, A, B, C, D, E, F, G will be turned on or turned off. For example, if my number is 0, it means that I will have 0, 0, 0, 0 at the input. What about the output? What happened in the output? In the output, A, B, C, D, E, F will be 1. A, B, C, D, E, F will be 1, and G will be 0. For 1, this pattern, this one, this one, this one, this one. But now I have to design a circuit to produce the A as the output. I look at to this column. And I find that only when my input is 1 and when my input is 4, my A is 0. My A is 0. So it means that I can actually design a circuit that recognize these 2 patterns, 1 and 4. But how can we find and recognize these 2 patterns? Using this circuit. I say that I want to have 1 at the output of my circuit, and I want to recognize P1 and P4. But we learned here for recognizing 2 patterns, if always is one of them is 1, I will have 1. But here, my output is 0. Now, in this case, I want to have 0 at the output. But I want to have these 2. I say that it doesn't matter. I can design the same circuit for the recognizing pattern. At the end, I can complement the output using NOT gate.